Folks, let's get started here. I'm happy to welcome Rob Simcoe here for our afternoon colloquium this week. Rob, as many of you know, joins us or comes to us from far down the subway line from MIT. He's the Francis L. Friedman Professor of Physics at MIT, also the director of the MIT Kavli Institute for Astrophysics and Space Research. He specializes in observational astrophysics with an emphasis on chemistry of galaxies, intergalactic matter in the early universe, but also heavily in instrumentation that leads to being able to do that science. He did his undergraduate work at Princeton, where he worked on development of a camera for the Sloan Digital Sky Survey. As part of his graduate work at Caltech, where he did his thesis on chemical enrichment of the IgM. He also worked on collaborating on a construction of a camera for the 200-inch at Palomar. He's from Massachusetts originally, from Westboro, and so following that work, he finally came back home, but inside 495, to go down on a Pappalardo fellowship to MIT. Following that, he joined the faculty at MIT. He's been the PI and project scientist for the FIRE IR spectrometer at Magellan. And in 2019, he was appointed as the director of the Kavli Institute, as I mentioned. And now he's the PI of 2 additional instrumentation projects that I think we probably will hear maybe a little bit about today. So all of these instrumentation elements complement the observational work that Rob has done such a broad amount of work on, and that includes work on cool stars in the nearby universe, discovery and characterization of high redshift quasars, intergalactic matter in the early universe, and today he's going to tell us about recent work on black hole growth and metal enrichment in the Reionization Epoch. So take it away, Rob.
All right. Thanks very much, Pat, for the nice introduction. It's good to be here. I pointed out to Pat as I was coming in that I was an SAO summer intern here in the REU program, giving a presentation here, and it must have been 1995, so that's many years ago. It's nice to know that all this stuff is still happening. I'm very grateful for that, the opportunities that provided. So why don't we get started? After all that talk about instrumentation, I'm going to tell you about JWST observations for most of today. Although I'm going to touch a little bit on instruments as well. It's just, there's 1 hour and we had to pick some things to talk about. And this is something that I often don't get a chance to discuss, but it's a really interesting story. I'm going to structure my talk as follows. So I'm going to start by reviewing, for those of you who don't do this on a daily basis, what are sort of mental images of what we call the circumgalactic medium. We can talk about whether that's a good word or not to describe what this is. But people have divided sort of the diffuse gas empire into circumgalactic and intergalactic and interstellar media. And so I want to talk about the sort of strengths and weaknesses of that model. And then I want to go on to talk about the first observations we've been able to make of this environment at redshifts beyond 5. So we could look at the gas earlier, but we've only been able to look at the galaxies since the launch of JWST. And so there's an interesting survey that I've been involved in that is helping to elucidate new ideas there. And then I want to talk about how these observations kind of change the way I look at the history of the construction of what we call the circumgalactic medium. And then along the way, I would call it a side quest. I'm going to talk a little bit about new instruments and observatories. But also early black hole growth, which is because we happen to be pointing JWST with a blind survey towards some of the most famous high redshift quasars. We learn quite a bit about them in the process for free. So just to review, there's a picture that's kind of emerged for what we call CGM, the circumgalactic medium, and the intergalactic medium. And these have really evolved over a couple of decades, and they were very heavily influenced by observations that were made with the Hubble Space Telescope very early on, for a couple of reasons. Most significantly, that Hubble Space Telescope had the ability to take UV spectra of low redshift quasars and could study the vacuum ultraviolet transitions of Lyman alpha and heavy elements ionized several times, like carbon-4, magnesium-2, things like this. And also, around the same time that Hubble Space Telescope was launched, large ground-based telescopes that had the ability to take optical spectra at resolutions of several tens of thousands emerged. And this is the resolution that's required to actually resolve the physical scale of lines on the Lyman alpha forest. You can get to several kilometers per second. Sort of 5 to 20 kilometers per second is the resolution you want to have if you're studying quasar absorption lines. And what emerged, when people looked at quasar sight lines that passed near galaxies, you would often discover that there was an enhancement of absorption at the redshift where the foreground galaxy lies. So this goes back down to 1998. So this was an observation with at that point, HST had just had its corrective optics put on, and it was using the faint object spectrograph, where people measured the equivalent width of Lyman alpha absorption as a function of some distance from the galaxy sight line modulated by the luminosity of that galaxy. It's basically a correction for the brightness and the size of the stellar mass. We weren't calling it stellar mass then because people weren't doing fits. But there was a sense that the strength of Lyman alpha declined as you go out to 100 to 300 kiloparsecs. There are mostly non-detections out here, but if you're inside of 100 kiloparsecs, you were always seeing very strong Lyman alpha. Later on, the same thing was true with oxygen 6. So this is a very influential paper that was written in 2011 by Jason Tumlinson and the COS Halos team, where they looked at oxygen 6 as a function, again, of impact parameter from a quasar sight line. So the quasar is behind a galaxy, and if you look at the redshift of the foreground galaxy, you discover that star-forming galaxies all detected strong oxygen 6, and galaxies that were not star-forming typically had weak or no oxygen that was hot and highly ionized. This would be gas at about 300,000 degrees. And so people looked at these and said, aha, like if you see enhancements of absorption around galaxies, then what's happening is the gas is just gravitationally bound to that galaxy, and what you're seeing are chance interceptions of galaxy halos along the line of sight. But at the same time, people were performing cosmological simulations, like the one that you see here. This was around the year 2000. This was one that was run by Renya Chen and Jerry Ostreicher at Princeton. And they discovered that these simulations, that sort of mildly nonlinear things, not collapsed galaxies, but filaments that had overdensities of sort of 1 to a few, that had not collapsed and virialized yet, but were just starting to sort of break away from the general cosmological expansion, that those things could reproduce the salient properties of the Lyman alpha forest at redshift 3. And the idea is that you have a quasar and it passes through, and basically the Lyman alpha forest is just chance interception of a quasar sight line with each of those filaments. And so people would argue about what's going on. Are these discrete halos around galaxies, or are what we're seeing is just peaks in a smoothly fluctuating density field? I think over time, this question has kind of resolved itself. And the answer is that both are right to a certain degree, and that the disagreement was because of the kind of nature of the observations. So I like to think, instead of just like the IgM and the CGM, I think of it as gas that you would call interhalo versus intrahalo. So the intrahalo gas is stuff that's bound to a dark matter halo, right? So it's not, you say that it's circumgalactic, but that's not really right. It's inside the dark matter halo still, so it's still part of that galaxy. And so that represents gas that's at 10 to 100 or even larger overdensities relative to the cosmic mean. You might call this the CGM, but I would call it intrahalo gas. And that's what's represented by those observations you saw of individual galaxies, whereas the redshift 3 Lyman alpha forest was indeed looking at interhalo gas, that it had smaller overdensities. And the reason that you were interpreting these differences had to do with the sensitivity of the observations, but also redshift evolution, right? As you go from redshift 3 to redshift roughly 0, the universe is becoming more ionized, not because you're getting more galaxies, but because of the a to the minus 3 scaling of density. And that makes the universe more ionized. And so what that means is that the lines that you see still at low redshift are the very strongest ones. And when you're at higher redshift, you can see things that are weaker because your average spot in the universe is a little bit more neutral. But it's also true that the observations of individual galaxies, these things had sensitivities of only 300 milliangstroms, whereas the redshift 3 Lyman alpha forest observations with Keck and high res were a factor of 6 to 10 more sensitive. And so there are just important differences, and we sort of interpret it that way now. Nowadays, COS is flying on HST, and you can actually do you can understand this in much better detail. And this is just a way of looking at this that I find kind of interesting. So now, instead of looking at just the the impact parameter in kiloparsecs, let's scale this in terms of the virial radius. So what we're looking at here, let me tell you how to interpret these plots. So this is from a stack of COS spectra of quasars that pass near 4,500 galaxies at sort of low-ish redshift, sort of a half to 1. And the way to think about these are individual profiles of Lyman alpha in terms of increasing distance in transverse separation from the quasar sightline. So this is from 0 to 1/3 of the virial radius. This is from 1/3 to 2/3, 2/3 to 1, going all the way out to 5 times the virial radius. And what you see is that there's Lyman alpha absorption essentially everywhere. That's the intergalactic medium. But indeed, once you get inside maybe 2 times R200 or R virial, that in fact the strength of absorption starts to go up. And that's confirmed again with Lyman beta, and you can do this down the Lyman series. But the point is there's absorption from neutral hydrogen, even spread throughout the universe, but there's a definite enhancement that happens when you get inside the virial radius of individual galaxies. And again, this goes out to 5 times R vir, right? So this goes out way further than you would expect a galaxy to directly influence its surroundings. The same is true of metal lines or heavy element absorbers. So on the right, I see here's doubly ionized carbon and 5 times ionized oxygen. It's the same thing. So we've stacked 4,500 galaxies in bins of increasing transverse distance. Now it only goes out to 2 times R200, so we're zooming in a little bit. But the same holds true. It's actually interesting for carbon-3. You see that there's an enhancement. Carbon-3 actually is all throughout the Lyman alpha forest, which is quite interesting. This is the favored ionization state of carbon. We just can't see it at high redshift for technical reasons that have to do with the Lyman alpha forest blending. But it's all around. It's very prevalent. But then again, as you get inside of about 3/4 to a half of R vir, then the metal enrichment goes way up, right? So there's some evidence that metals are outside of galaxies or they're associated with other things, but when you get close to a galaxy, you're probably seeing local enrichment from that object. And the same is even more true of oxygen-6, where you're not only seeing the metals from that galaxy, but you're probably also seeing some local heating, which is elevating the temperature from the sort of equilibrium of 10,000 degrees to a few 100,000 degrees. Whereas outside of R vir, we actually don't see statistically significant evidence of oxygen-6. So all this just to say, when you get close to a galaxy, you see this metal enrichment. And then in hydrogen, you see, there really is a special area that's within about a half of the virial radius of galaxies where you're seeing localized evidence that those galaxies are influencing their surroundings. And this has led to a sort of prevailing view of what the circumgalactic medium is. That sort of area, that special area that's within half of a virial radius or so, loosely defined, is what we call the CGM. And I think of it as loosely bound intra-halo baryonic matter. So yes, it's around galaxies, but it's around the galaxy disk. It's still inside the halo. Not only that, if you look at the velocity offsets of that gas from the redshift of the systemic redshift that's established by stars in the ISM, typically the velocity shear is not that much, and it implies that on the whole, at low redshift, this gas is gravitationally bound to its host galaxy. And it's very clearly enriched by heavy elements produced locally. The ionization state is probably produced through some combination of heating and ionization. Even though it's close to a galaxy, most of the ionization is coming from the metagalactic background of the integrated galaxies in all directions. And so it becomes, there's sort of an interpretation that's emerged where people think of this as a cycle, right? So that when a galaxy forms, a halo happens, matter accretes into that halo that's pristine, a galaxy forms, and then that galaxy starts spitting out heavy elements, it starts producing ionizing radiation, and then those baryons cycle through, and through each successive generation, the gas becomes more enriched with heavy elements. It's actually quite a nice story. It's very elegant. And in that scenario, so I don't know if they still teach the closed box model of chemical enrichment in ISM courses. I always thought this was kind of a fun one. But the idea would be that this is a closed system, right? It's a gravitationally bound system, and the gas is going in and out. And through each generation, it's determined by some, I guess there's an instantaneous yield approximation, and then the stars yield the heavy elements, and then they enrich the CGM. So that's all fine and good. But as I said before, we've never been able to study how this area, the special area that's enriched with heavy elements, was formed in the early universe, and how did it start? So what's the first few chapters of that story? So we've been able to study heavy element enrichment using quasar spectra for 20 years or more, since quasars were first discovered by the Sloan Digital Sky Survey beyond a redshift of 6. Once we were able to take infrared spectra of sufficient sensitivity, then those could be used to measure heavy element abundances. But we haven't had access to those galaxies because they were just too faint. But here's just an example. This is not one of the earliest quasars discovered, but it's one of the brightest. And what this shows you, so this is one at redshift 6.33 approximately. And all of these lines, that you see below the continuum, those are not noise. Those are absorption lines, usually multiplets that we use to identify at a range of redshifts between 0 and 6.327. For this paper, they were focused on fitting the emission lines, but I'm always interested in these absorption lines. Like this is probably, for example, an iron 2 absorption system at redshift 4.5 or 5. This is probably like the 2600 and 2586, right? So you start to learn these patterns. Out here, you see the magnesium 2 emission line, and then these absorption systems you see out here are magnesium 2 at a redshift of beyond 6, right? So you can find these heavy elements, no problem, right, no problem. It's not easy. It takes long integrations on big telescopes, but it's possible, and we've been doing it for a long time. So, ooh, that's nice. Yes. It's very peaceful. So what do we know about heavy element absorption that occurred in the first billion years after the Big Bang? One of the things that is unfortunate, but is that I have to disclose and acknowledge up front, is that we'd like to study metallicities and heavy element abundances. But for these purposes, we don't really have access to the hydrogen information. So we can't measure a heavy element abundance, not because we can't measure the heavy elements, but because we can't measure the hydrogen. It's too bad. But the Gunn-Peterson effect, which is so interesting if you're studying reionization, is bad news for us. Because at all these redshifts of interest, it's basically, the on-resonance absorption of neutral hydrogen is too strong. It just overwhelms you. And so you can't distinguish individual lines. But you can count absorbers and measure the relative abundances of different ions. And there's a few, there's many things we've learned, but these are ones that are interesting to me at least and relevant. One is that the carbon-4 number density is in decline as you wind the clock backwards. So again, this is going up in redshift and back in time. You see that as you go out to about a redshift of 5, the number density, so the dx is a weird thing for absorption line aficionados. You can think of that as like a co-moving volume density, right? It's basically a dn dz, but you've changed dz to something that's a co-moving value, so that things that you're using a constant yardstick at different redshifts. So it's roughly constant, it changes by maybe 30% as you go out to redshift 5. And then from redshift 5 to 6, the number density of these highly ionized, triply ionized carbon goes off a cliff. And it's actually quite rare to see a carbon-4 system beyond a redshift of 6. It's unusual and interesting, which is quite the opposite. Like the carbon-4 dominates absorption line systems below a redshift of 5. They're the most common by far among the metal line systems. So you might say, aha, like we've found a redshift that corresponds to the epoch of first enrichment of the universe. But that's actually almost certainly not true, because for two reasons. One is that it could be going away because there's fewer heavy elements, but it also could be going away because the ionization balance favors other ionization states of carbon. And we can look at other ions that have a lower ionization potential, like magnesium 2. And when you go out to higher redshift, this is that same quantity, dn dx. This is for sort of garden variety magnesium 2 absorbers. These are for the very strongest ones. So the strong ones are interesting. They go up in density, or they go up in frequency, but then as you go to higher redshift, they tend to go away in a way that seems to follow the star formation rate. But these sort of normal magnesium 2s that have middling line strengths, they stay the same. And as if we go to increasingly higher redshifts, they don't go away. And so what that means is that this doesn't correspond necessarily to the first era of chemical enrichment from stars. There's probably an ionization effect going on that's not producing carbon triply ionized, but that the metals are out there. And we can see this, that's sort of emphasized by this third plot over here to the right. So this is as a function of redshift. You're looking at the ratio of carbon 2 to carbon 4. So it's the same element, but it's different ionization states of that same elephant. So things that are in red up here have stronger carbon-2 absorption than carbon-4. That's very unusual at low redshift. You see there's a few like that, but if you were to extend this further to the left, this would basically be empty over in this quadrant. And then things in the green here are where carbon-4 is stronger than carbon-2. And somewhere around 5.5 to 6, like these kind of flip, so that you're actually seeing more neutral systems. And there's some very weak evidence that there's more oxygen in the neutral ground state also. There's a bunch of these sort of low ionization lines that just kind of go out as far as the eye can see, whereas at low redshift, everything is very highly ionized, like the hydrogen. For some reason, well, some people will say that this means that the circumgalactic medium, they talk about this as being reionized around this redshift, because it's a little bit later than the hydrogen was reionized, right? Hydrogen was reionized somewhere out here, but you need somewhat harder photons to ionize these heavy elements. Okay, so that's kind of where things stood. Now let me talk about what we did with JWST. So I was involved in a survey called EIGER, which stands for Emission Line Galaxies and Intergalactic Gas in the Epoch of Reionization. So this was a Cycle 1 GTO program, and we devoted 100% of our time to slitless grism spectroscopy with the NIRCam instrument. This was originally envisioned as just a blind galaxy survey, but we had persuaded the rest of the team to point the telescope and do not just a galaxy survey, but just point it on fields that have some of these famous and great high redshift quasars that are the best and brightest. So the way that we performed the survey is as follows. So the NIRCam slitless, NIRCam in general, but we were using it in this mode, but it's always the case that it has two modules, and they're separated on the sky by a gap in between them. And we wanted to have continuous coverage so that we didn't miss any objects along. And so this was a 120-hour program. After the overheads, we had about 20 hours per pointing for 6 fields. Actually, we had a little bit more than 120 hours. And so we did 5 hours per pointing and 4 pointing. So the first one, the quasar would be centered weirdly on this sort of lower corner of one of the modules. And then we would move the telescope and observe it in this orientation. So the red is the active one and the blue is the previous observation. And then we would move and then observe in this orientation, and then move and observe in that orientation. And so what we're ending up with in the final analysis is a continuous mosaic that had 20-hour depth because every pointing covered a little 40 by 40 arcsecond region in the middle. And then there's weird patterns of greater or lesser exposure depth that are sort of off the center, but it sort of gets shallower as you move away in standard fashion. So 20 hours here per field and 5 hours per field in these sort of outrigger areas. And the total area that you get on the sky is about 10 co-moving megaparsecs by 5 over h. So the central area here corresponds to a box that's about 250 kiloparsecs on a side, which is, you probably might have, the astute listener would have noticed that that's a bit bigger than what we called the sort of zone of influence of low redshift CGM absorption line galaxy associations, right? So I said it goes out to 1 to 200 kiloparsecs, and so we decided to go out to that same distance. And so there was a trade-off between how big this sort of central deep area is and what the overall field of view was going to be. And that's what we landed on. For those of you who aren't familiar with the slitless grism, what we were doing was selecting for emission line objects. So it's a blind survey. Because it's slitless, we get everything in the field. But we were looking for oxygen 3 and H beta at redshifts of 5.3 to 6.9, which is determined by the blocking filter you use. We used the F356W blocking filter. And it looks like this. So we took 3 photometric bands. So we took images in F356W 200 and 115. And then combined that with the spectroscopy, where you basically take out, you have the 356W filter in, and then you put the disperser in, and then you trim it with the filter. And so you can make a color image from the 3 photometric images that we have. And then this is what the data look like after you insert the disperser. And so now the dispersion, every single object in the field is dispersed and is overlapping in wavelength direction. So we spent, it wasn't exactly known by our team and others. We were reasonably confident that you could disentangle and disambiguate all the the objects in these grism spectra, but it hadn't been done before, but we just decided to go for it and put all of our eggs in that basket. And it worked quite well, thank God. So you can see kind of what it looks like. So here's the two arrows here are pointing to two Redshift 6 objects. And then if you look at the same postage stamp, you can see these three dots here that correspond to that object, and then these three little features here that correspond to that object. And so these two are the oxygen 3 doublet, and then that's H beta. And then we apply a high-pass filter to basically remove the continuum of each of the foreground objects. And then you can run just photometric finding algorithms, or you can predict based on the photometry where the lines should appear and go and look there. We sort of did it both ways. But you just look for, you pattern match against this triplet of things. And then that allows you to figure out what the redshift is unambiguously. It was absolutely delightful when we had no idea how well this was going to work when we started, and it was just shocking when the first data came in and we found 100 objects in that first field. We were just absolutely stunned. I will always remember that period. That was certainly a career highlight. I will mention, so because we're taking spectra of everything, it has the advantage that you're not worried about doing your photometric selection correctly or that your slit assignments are colliding and things like that. But the cost of that is that the depth is less than you would have if you're using NIRSpec in the MSA mode. So that was our trade. But we didn't even know where to point things. Like we didn't have deep enough images. It was cycle 1. We just decided, just open it up and go. Here is this is the broadband image that comes from here. It's actually it's too bad, like in a projector kind of thing, this doesn't display as well as it does on an LCD or others. But we had quite deep images. So this is the high redshift quasar of note. So this is the same quasar that I showed the spectra of before. And so here's our 3 NIRCam bands, color composite image. We also have HST filters that are not shown, mostly to filter out low redshift contaminants. And I'll just take a moment here to point out that this is not like, if you were constructing the perfect survey to do the kind of an analysis and the science I'm talking about, EIGER might not be exactly what you would do because we picked sort of randomly based on just the apparent magnitude of the background quasar, which shouldn't necessarily be a discriminant for what the sort of foreground absorbers are doing. But we did have some knowledge as to which sight lines had quasar absorption systems in them already. And we also picked things just because they were at high redshift, and there was one that had a really long trough in the Gunn-Peterson. Like, it was a compromise how we chose the fields. And so eventually somebody should go back and do this with a truly blind set of these things. But again, we sort of felt like it was a brand new observatory. We wanted to guarantee some yield. And so we went for these particular fields. But just, in the interest of full disclosure, I don't want to pretend it's perfect, but so just, I think it's pretty good, but just keep that in mind. And if you see troubling things that I'm calling out, please don't hesitate to point that out to me. So that's our field. So let me put circles around all of the objects that are in the redshift range of interest. So we observed 6 different fields. As I said, there's 1 to 200 objects per field that were in the right redshift range. Altogether, those 6 fields had 936 oxygen 3 emitters. But importantly, 677 of those were at a redshift that was at or lower than that of the quasar. The ones that are behind the quasar are interesting for other reasons I'll talk about. But I'm particularly interested in these. And that's enough that you can start doing some interesting science. Here you see, these are color-coded by redshift. And so essentially things that are white are at the redshift of the quasar. Things that are blue are in the foreground, and things that are red are in the background, more or less. And again, the quasar's at that same spot. It's just you can't see it because there's other objects at the redshift of the quasar, which is interesting in its own right. Let's see, I'm exactly a half hour in, so let me stop for just a second and see whether people have any things that they want clarification on, questions. We did not target any lenses as part of the survey. We uncovered some lenses. Yes, there are accidental lenses. I think in every single one of our fields there's some random galaxy lens. we haven't really, there's more to look at than we could possibly do given the size of our team, and so we haven't really looked into them. But my sense is that most of these, to first order, every lens is at redshift of 0.7, and everything else is behind it. So I think they're mostly down there, and they didn't come out in the slitless spectra, unless you happen to get a Paschen line, because this filter is not so great for looking at things at low redshifts. I think we're going back to observe it with other grism filters, and you'll be able to get all of the different redshifts, and then it will be better. But yeah, we only got like the lucky ones, but not these big spectacular ones. They were like little pairs that look like Einstein rings. Yep.
Did you use two grism positions as suggested or not?
Good question. So you always wonder whether you've got your wavelength solution correct or whether you've associated the right object with the right thing. So we did not do the orthogonal grisms. So the instrument has the ability to disperse, if you go back, it can disperse it either right to left or up and down. And so we did not do the up and down, even though that was originally recommended. We decided that if we have a triplet, we can find it this way, but it's also true that of the two modules, this one, I think this one disperses right to left, and that one disperses left to right, or vice versa. I can't remember which is which. But they're opposite each other. And so for the areas of overlapping pointings, we have opposite dispersions, and we were able to sort out a lot of objects that way and gain confidence in our redshift assignments. So the answer is like no and yes. No, probably like not what you were thinking of originally. I don't know that many people are even using the the orthogonal dispersion anymore, but that's a subject for more discussion. Other questions? Okay, if not, I will move on. Let's see. Okay, let's talk a little bit about what those galaxies are. So what are the kind of galaxies that emerge when you point the slitless grism for 20 hours in one direction? The way I like to think about them is what we call a galaxy at redshift roughly 6 is more like the small Magellanic Cloud, if you want to think about it in terms of things that you know. Using prospector fitting, thanks to all of you who've developed prospector here, this is a very useful tool for us. So we did those fits, and also thanks for including emission lines, because the emission lines of these are so strong that if you don't include those, you get ridiculous answers. So yeah, it's slow, but we just run it on the big cluster, so that's all right. So the stellar masses that we got were sort of from about 7.5 to maybe 10 to the 9 in log of the stellar mass. We can measure the star formation from H beta, or we can get it from the prospector fits. I trust the H beta a little bit more, but there's like a sort of ladder that you have to do to get from H beta to a star formation rate. But still, the answers that you get are sort of 1 to 10 solar masses with some scatter. And so they're kind of believable answers. On the right here, I show the inferred, so these are observed or pretty simply derived quantities, and these are very inferred quantities on the right-hand panel. So this is the log of the halo mass that you would have if you do stellar abundance matching to this, abundance matching of halos to the stellar masses derived over here. These were done using the universe machine code from Peter Berruzzi. And then if you turn these halo masses into a virial radius, this is just a formula that gets you from here to here, so it's not surprising that there's a very small scatter. The only scatter is just that these things are at slightly different redshifts, right? And so that introduces some of that. But the point here is that the halo masses are sort of 10 to the 10 to 10 to the 12, maybe. But if you look at the virial radii of these things, it's typically like around 20 proper kiloparsecs. And this is a point that I want to come back to. So it's for two reasons that this happens. So the virial radius, which I use these interchangeably if you haven't figured that out yet. So the formula looks something like this, and it goes as the halo mass to the 1/3 power. So as you're going down in halo mass, it's the case that the radius of influence gets smaller. But there's also this factor of h of z to the -2/3. And a thing that keep in mind that's very different from the low redshift circumgalactic medium is that h of z is about 700 kilometers per second per kiloparsec when you're at redshift 6. And so we all kind of know that, but it's interesting how it plays into this formula here. So actually this is as important or more important, because what it says is, if you're outside R200, you're in the Hubble flow. If you're inside R200, you're in the galaxy, sort of. It's a very colloquial way of thinking about it. But you don't have to go very far before you enter the Hubble flow if it's moving at 10 times the Hubble expansion rate that you would have at redshift 0. And so all that means that your R200 is about a factor of 10 smaller than it would be for an L-star galaxy at redshift 0. These things are very different beasts from what we're used to. So think about it this way, right? So here's the Milky Way and the large and small Magellanic Clouds, just drawn on PowerPoint, roughly to scale in terms of the sizes and their separations from each other. And then if you looked at the kind of galaxies that EIGER finds, and I try to draw them roughly to scale, this is just a bunch of postage stamps of these things. I'm not trying to match stellar masses or anything, I'm just like matching them by physical size. So this is what they would look like on this diagram here. And you can see the thing that they most resemble is this, right? I think this is something that, for people who work on these high redshift galaxies, this is kind of natural and expected. But again, I'm always trying to sort of make a mental image of what it is that I'm looking at. The other thing that's quite interesting, these are not foreground chance, things that are chance aligned along the line of sight. A lot of these things are merging at high redshift, which is, as expected. All right. So for me to understand this, like that all kind of makes sense. And if you've looked at cosmological simulations of structure formation, it sort of kind of all holds together. And so let me play the one movie that I have, which is from the FIRE collaboration simulation of the formation of a single galaxy in one halo. This dot is going to expand to become a circle that represents R200 for this galaxy as it forms. And they're just going to follow this as it goes forward. So this starts at redshift roughly 20, I think, and then you see it expand. Now we're at redshift 3, 2, and then the size of this galaxy is growing, so RVR is growing. And then it starts to eventually accrete enough matter that it forms into a galactic disk. And you see that there's some feedback that's elevating the temperature inside and then outside the halo. But eventually it settles into what looks like a disk that we know and love, along with some satellites. And then when people think about the circumgalactic medium, remember that mental image that I had painted for you early on that corresponds to a redshift of something like that, right? And so when we think of that, fine, there's a galaxy in the middle of the halo. R200 goes out to hundreds of kiloparsecs. And what we call the circumgalactic medium, or the loosely bound intra-halo medium, is this stuff that's not appearing so well in this color scheme, but you can kind of see it, right? It goes about halfway out to RVR. And then if you shine quasar sight lines through that, then you'll see small velocity offsets from the central host galaxy. And it makes sense to talk about the host galaxy in some of these cases. And then there's the gas that surrounds the host galaxy. But when we do this EIGER survey with JWST, we have to wind this all the way back to about there, right? So that's, what's the galaxy, right? It's some combination of all this stuff is the future galaxy. But when we go and find things in the slitless grism, what we're picking up on are all these little knots that you have along here. And you can call them galaxies, but they look like the Magellanic Clouds, and they each have these tiny little virial radii. And so it's important to think about that. And the other thing, too, is if I just move this back and forth a little bit here, and you look at the right-hand panel, you can see that this is just the point at which some of these little halos are starting to heat up their surroundings, and presumably they are also injecting interstellar material and heavy elements into their surroundings as well. But it's that mind's eye picture that you can see where I'm getting at. I'm trying to break your mind's eye picture of what people think of when they talk about the circumgalactic medium, because it's just different at high redshift. Now, before I go back to sort of talk about some more quantitative results, that's just the picture I want in your mind, I want to point out that we've done a lot of other kind of science along the way, because you get all this interesting stuff for free when you point the slitless grism in a particular direction. Some of these things are around quasar science, others science is not. So one of the ones that I think has been pretty impactful is the paper that discovered these things called little red dots emerged from EIGER and Fresco, that we were the first deep survey that covered enough of the sky to find these things. And they're taking up a lot of the airwaves at the moment. These are things that look like point sources, but when you look at them in H-alpha or other blind grism surveys, you realize these are not normal point sources. They have very broad lines, emission lines. And over time, it's been a mystery to figure out what they are, but there's sort of a general consensus emerging that somehow these things are important for us understanding how black holes grew. And it probably represents some sort of obscured phase of black hole growth in the early universe, and that these things are much more common at high redshift than they are locally. So that was kind of a fun, unexpected surprise. So another one that I've particularly enjoyed is looking at the correlation function and duty cycles of luminous quasars. So the argument goes as follows. So if our quasar is at the center of this field, all the galaxies that are shown with circles here are at the same redshift as a quasar. So this is an enormous overdensity around the emission redshift of that quasar. And then we can use this to study the cross-correlation function between galaxies and quasars as projected onto the sky, or projected through the screen in this case. And from that, you can deduce what the halo mass is of the galaxy that's hosting that quasar. And so here's the transverse separation versus the projected cross-correlation function as a function of, so you compare that to dark matter-only simulations of different halo masses, or you count halos in those simulations and figure out which ones have the same amplitude and shape of the cross-correlation function. And it turns out it's about 10 to the 12.5 for the average supermassive black hole hosting UV luminous quasar. These are these crazy bright quasars. That's how we chose them for the survey. We also get for free the cross-correlation function of the oxygen 3 emitters. They're in halos that are 3 times 10 to the 10 solar masses. But one of the things that's interesting is you can count how many 3 times 10 to the 12 solar mass halos there should be in the universe. And the answer is a lot more than bright quasars that we find at a high redshift. They should be much more common. And what that tells you is that we think probably all of those have black holes in them. And it's just that they're not shining in a UV luminous phase. And so the number density of bright quasars to halos of the same mass is 4 times 10 to the minus 3. And that's the implied duty cycle, which means that if these things are growing to 10 to the 9 solar masses, which is much bigger than they have any right to be, they must be doing it in some way that doesn't involve being UV bright a large fraction of the time. It's a kind of an indirect argument, but a neat one. I like it. Other things, so we detected the host galaxies of some of these quasars. So if you subtract the PSF, so this is in the 3 bands that we observed, and then if you subtract a model of the PSF from each of those, you end up with these residuals that correspond to estimates of what the host looks like. And you might say, I either believe that or I don't. But the thing that's most interesting is that actually the host should be probably bigger than this, not smaller. Because when you measure the stellar mass of the host, it's a bit too small for what you would expect it to be based on the typical relations at lower redshift of the stellar mass, the bulge mass or the stellar mass versus the black hole mass of a host. These are these well-known Cormandy and other relations. You find that the black holes are a little bit overmassive. And you can argue about whether this is, again, a perfect sample for this or not. I would say it's probably not. But this is what we got. And if you were following the normal low redshift relations, the galaxies would be more massive than what we observe, not less. And so the fact that we detect small galaxies becomes interesting. So here's, at redshift 4, some examples of circumgalactic medium also. So one of the things at redshift 4 is you can see all this kind of structure in galaxies. So this is, each of these clumps is part of the same galaxy that's showing H-alpha at different velocity shears, and there's a tidal tail that appears in H-alpha. And then you look over the corresponding quasar sight line, and you see magnesium 2, iron 2, aluminum 2, magnesium 1. But one of the things that's quite interesting here is that we find strong absorbers often near these merging systems are the strongest ones. But the other thing that's quite different from at low redshift, remember how I said the velocity shear between absorbers and galaxies was very small, so it always implied that the gas was bound. In these high redshift ones, the velocity shear is much larger, and actually the gas is moving beyond the escape velocity, which means that it's either outside the galaxy or it's leaving, or something else, like maybe there's another smaller galaxy that's nearby. and we'll return to that. So that's all kind of fun science that we had along the way. But my particular interest was in looking at interactions between galaxies and the intergalactic medium. So that could be radiative feedback, it could be chemical feedback. So here we show, this is actually the location. So this is the line of sight going from left to right. So this is high redshift. This is towards the Earth going off the right of the screen. This yellow dot here is the redshift of the quasar. And so we have a spectrum that goes along this sort of red arrow. And we know what the transmission function of the IgM is in neutral hydrogen. That's from our quasar spectra going towards Earth. So this is what it looks like. And you see that it's the fact that you see transmission here means that the quasar is ionizing its surroundings out to about 10 megaparsecs. And then you can see these green dots are the locations of all the oxygen-3 absorbers that we found along that line of sight. And the thing that's interesting, you see little clumps of them. So there's one here, there's a big one around the quasar, and then there's some behind. And we can look at interactions between galaxies and the IgM. So a beautiful way that you can see radiative feedback. This is a fun one that we didn't really expect, but it was kind of a surprise. So there was a big cluster that included some bright galaxies behind the quasar. And we realized that you could take JWST and observe these. And then instead of using the quasar to look at the foreground, you could use these galaxies as the background and look at the radiative feedback from the quasar itself. And so here's an example of a spectrum of a galaxy from this overdensity. And at the point where it passes by this quasar, you can see that there's transmission in the otherwise completely saturated Lyman alpha forest. And what that shows you is that the quasar has ionized its surroundings, and you're seeing it in the transverse direction as you go by. So this is the 2D spectrum up here. You can see clearly that there's non-zero transmission, and it's not centered on the redshift of the quasar, and there's an interesting geometric reason having to do with the way that light propagates out from the quasar and then towards Earth. There's a light cone that surrounds it. And from that, you can deduce the geometry that if you look at a bunch of galaxies, you can figure out how long light has been propagating out in the transverse direction, and also whether it's propagating in an isotropic way or in a directional way. So that was kind of a cool side project. There's another one that's kind of fun down here. If you look at here, this magenta line is telling you what the transmission is of the IgM, and you see that there's a little bump in the transmission. So this is the famous Gunn-Peterson trough. So there's no transmission where there's no galaxies, and then you see a little transmission, and then there's a set of galaxies that's nearby. And so, so we're certainly seeing evidence that there's no quasar here, the quasar is up here, but individual galaxies are starting to reionize the universe, and we're finding that what we think are the agents of that in certain cases. You know, this is the best example of that. It's usually a statistical measurement. The other thing that's neat, too, so the red dots along here show you where there's carbon-4 absorbers, and then you see that several of those are around where there's little groups of galaxies, and that's true here as well. There's some carbon-4 absorbers that don't have galaxies as well. Okay, so let's drill down a little bit on this. So at these high redshifts, you know, I was interested in the chemical enrichment around them, and it turns out that even though there was not necessarily a prediction about whether we would or would not see these associations, at high redshift you still see lots of cases where there are galaxies and heavy element absorbers in proximity to each other, at the same redshift to within a few hundred kilometers per second, and at impact parameters of 1 to a few hundred kiloparsecs. So like low redshift, you're getting matches between galaxies and absorbers at sort of 20 to 200, I would say, and a velocity shear of less than 1,000 kilometers per second. But if you look at these, let me tell you how to interpret these figures. So these are 3 different fields of our 6. And each one of these fields, so I've drawn circles around galaxies that are that match the redshifts of known absorbers to within 1,000 kilometers per second. And the color of each circle indicates its redshift. And these horizontal lines indicate where there's absorption line systems, the heavy element absorbers. And so filled circles have a metal absorber at less than 1,000 kilometers per second, and the open circles have no metal absorber. And the size of that circle is equivalent to its virial radius. So the thing to point out is a few things. So if you look at this center panel, so there's a very strong absorption system here at redshift 5.72. And then you see all these green circles here. There's one that actually seems to cover the sight line. So the quasar is at 0, 0 in the center of each of these plots, there, there, and there. And so that one actually covers it, but actually there's many more galaxies that are at the same redshift. You almost always see more than one. And then there's many important cases at very high redshift especially. So here's a system at 6.17, and there's 3 galaxies at the same redshift. There's one here, there's one here, and there's one here. So there's multiple galaxies, but none of them is covering the sight line, meaning that the sight line's distance is much larger than the virial radius of that galaxy, which means that if the metals came from these galaxies, they're outside, like they've left, right? They're no longer gravitationally bound. By construction, if you're outside of R200, you're not inside that galaxy. So, you can kind of like look with your eyes and squint and see, though, here's a redshift 5.5 system, and you can see that there's 4 galaxies here at redshift 5.5 that are near but not quite overlapping the sight line. So if the heavy elements that we see in strong absorption came from those galaxies, they've left, or something else. But this is kind of the typical way that I think about these now. You could say, well, is this just a random circumstance? And the way I would look at it is by generating the cross-correlation function between galaxies and absorbers. And here you can see, so here it is. This is in physical kiloparsecs, transverse separation. This is the cross-correlation function of carbon-4 systems, and here it is for magnesium-2. The size of those halos of the same galaxies is shown in a distribution here. So things that are blue are inside the galaxy halo, and things that are outside of this blue shaded region are outside of any known galaxy. And what you can see is that there's a clear correlation between, there's a clear clustering signal between galaxies and absorbers, so that the metals congregate with galaxies we can observe, but in many cases, the metals are outside of those galaxies. And a different way to think about it is, this is just a sort of mind's eye picture that I'm trying to draw here to tell the difference between EIGER and like COS halos. So here, the red circles are drawn for the real impact parameters and virial radii of COS halos galaxies. And then this 0 vertical line shows the way that the sight lines pierce those halos. And this is kind of the standard survey that was used to draw the picture of what the CGM looks like at low redshift. And the EIGER galaxies are shown with their proper impact parameter in R200s. This is not the whole sample. This is the first 2 sight lines because I haven't remade this figure since then. But you can see it's just like qualitatively different, right? We're looking at different objects. And I just think back to that simulation that we showed before. You're seeing the things that are future L-star galaxies or large galaxies, but they haven't assembled yet. But we were already seeing the heavy elements that have emerged from these things or other galaxies that are near them. You're not seeing things that are bound inside a much bigger halo as you do at low redshift. Let me skip this over. We can go into the, I want to get to a couple last punchlines. This is just saying, we don't see, we tried worrying about, are there things that are hiding under the PSF of the quasar, so we just subtracted that off, and we don't see any evidence yet that there's things that are hiding there that we're just missing, because you have to look at very small impact parameter. But something that's kind of interesting is you could just ask, look, we have an estimate of the age of these galaxies that you get out of Prospector, or you can just divide the stellar mass by the star formation rate and get a sort of order of magnitude age, and say, have these things been forming stars long enough to originate in that galaxy and then cross the distance that it takes to get over the sight line? And the answer is generally no. You do have to account for a few things. So there's, when you integrate this equation out, it's not just that you're fighting gravity, but you're fighting this term that's called Hubble drag, which doesn't matter that much at low redshift, but when h of t is 700 kilometers per second per megaparsec, you do. And so we have reason to believe that the winds are leaving at about 120 kilometers per second from these, based on blue shifted absorption lines. And what you find is that if you let these winds go for long enough, they go sort of 30, 40, 50 proper kiloparsecs, not 150 to 200. So here, a way of looking at that is to reach the sight lines that we have in the EIGER survey, you'd need to kind of reach this dashed red line. And if you launch these at the times that these galaxies form their stellar populations, and then you observe them at the epoch that's shown with this sort of green shaded region, they only get out about halfway to the distance that they need to. And then this would be after, like what happened, we got interested in the question, what happens to these winds afterwards? And the answer is like some of them fall back in and some of them merge into the Hubble flow and just keep expanding, carried by the universe. But this is like a super toy model, so I don't want to overinterpret it, but I think that it doesn't necessarily pass the smell test to say, oh, like, these galaxies produce these metals. And so you could ask, like, where do they come from? Well, the metals are embedded in the same structures as oxygen-3 emitters, but they're outside the galaxies. So are they lower mass galaxies that we just don't see? Like, that's the usual interpretation. And that's possible. So if you just calculate the cross-section, like how many do you expect to see, like just drawing a bubble around each galaxy and then counting up the luminosity function, how many should you see? So you would expect to see 2 to 3 absorbers from the galaxies of the magnitudes that we have in the EIGER sample. But as you go to fainter galaxies, the number of galaxies is going up faster than their cross-section is going down, so that they will actually produce more of these. And so if we could get down to 30th magnitude or so, maybe. But we don't know. Those things would have stellar masses of 10 to the 6 or a few times 10 to the 6, so those are pretty small. I've also become interested in these objects that people have found here called NIRCam dark and dusty galaxies. These are things that you don't see at all in NIRCam, but they get picked up in ALMA. There's an example of one of these kind of things that's produced an absorption system. There's one that I know of. But if this becomes common at high redshift, it might be a different way of hiding systems that are very close to the sightline. And I will mention that's increasingly common. So we're doing another survey towards one more sightline with the quasar at redshift 7.5. And there's an example here of an absorption system at 7.37 that's got 15-ish oxygen-3 emitters. But they're at very large impact parameters, so they couldn't plausibly be the things that are producing it. But it's the same structure, and it's based around a huge merging system. But that's, the sightline, the merging system is up here, and the sightline is 500 kiloparsecs away. So there's got to be something else producing these. So that's kind of where we are. I think the point is that I want to sort of disabuse you of this idea that, the CGM as you go to arbitrarily high redshifts is just little galaxies and stuff that's inside their halos. It seems like the metals we see are outside the galaxies we see. We can talk about, so Pat mentioned that I build instruments. That's actually probably what I spent more time doing than this over the last couple of years, but I just decided it'd be fun to talk about this. So many of you know that we commissioned the LLAMAS instrument. It's an integral field spectrometer. It's been on the telescope for about 10 months. This is a big accomplishment for my group. I'm very proud of it. So LLAMAS, the spectrographs are here, and there's a fiber-fed IFU up here. This really doesn't help the particular science that I'm talking about today, so I'm not going to talk any more about it, other than just to say, please congratulate Gabor Firez if you see him on this. I'm happy to report that the light goes through it. You never know when you build these things if that's going to happen or not. It seems like it's pretty sensitive, and it goes way down to the blue, and it's a capable instrument. I'm happy to talk about it with folks who are interested. Other instruments, so another bit of news that I'm very pleased about is that MIT just announced last week that we're joining in construction of the Giant Magellan Telescope, and this is a big milestone for us. We're pleased to be joining with Harvard and SAO in this endeavor. This is a big deal. I think GMT actually really can advance high redshift science. So LLAMAS is a wonderful instrument. It's going to be great for low redshift CGM for follow-up of things with Rubin and whatnot. But I think GMT has the ability, if we play our cards right, in the SWIR bands around a micron. JWST is actually not that great around a micron. It's like okay, but it really suffers from read noise. And if you have a giant telescope and you build the right stuff for it, I think it could be quite powerful. And I don't want to say too much about it, other than just to say we're going to plan a workshop to discuss this kind of phase space. So a lot of the instruments were planned, before JWST launched and before all these things were imminent. It's also true that everything that happens at high redshift requires the infrared, but all the existing IR spectrometers on ELTs, if you look, this is like a highly biased landscape of coverage of different telescopes and what their instrument suites cover. But at least at GMT, these things that have dotted lines around on them require a highly functioning AO system to deliver on their science. And so we have to think about what about the parts of the sky that will not have that, or how long it will take to achieve that. We haven't really done a lot on that at MIT, other than that we're designing new optical relays that allow you to access different instrument ports on here, because that's kind of a general purpose thing that the observatory needs. And then we can come back and talk about the instruments at a later time. So let me skip over this one and just kind of go to my final slide. So here we are at Magellan. I'm just showing that picture because I like it. So the things I'd like you to take away from this talk. So slitless grism fields and surveys in these quasar fields just yield an extraordinary amount of science. We haven't even scratched the surface yet, and it's really fun to work on it. It was just a real thrill to work with JWST in its first year. Things we're learning, so it seems that there's an early emergence of a metal-enriched intergalactic medium, meaning things between the halos of galaxies that we can see. That's happening, and we can see it directly. Along the way, we're measuring quasar halo masses. We're learning about their host galaxies, the duty cycle of quasar activity, which is low considering the mass of these black holes. We're measuring light echoes of quasars and their surroundings, discovered little red dots, many more things. And what I'm encouraging you to do is just let go of your low redshift paradigm. Just let it go. It's accurate in the low redshift regime, and it's important, because this is the end state, like the equifinal end state of how galaxies end up. Result in this picture that we've learned, and I think it's important and accurate, but something very different is happening in the very early universe. And it's not just an L-star galaxy surrounded by an enriched halo. It's a bunch of little things that will in the future become an L-star galaxy or a cluster of galaxies, but they're spitting things out. So at redshifts beyond 6, the heavy elements look to be in galaxy groups, not in individual galaxies, or at least the ones that we see. In the central galaxies, will grow, as we saw in that simulation, but they grow from mergers after the enrichment of the inter-halo medium is well underway. And that the observed heavy elements that we see are unlikely to come from the observed galaxies. They're either from faint companions that we don't quite get, or from things that are dark to JWST because they're a very different mode of star formation that involves a lot of dust. I don't know which those are. This dust thing is so new that I don't think we know enough about the prevalence of those to say which of these is more likely, but it's interesting. And then I'll just say that for this particular science, I love LLAMAS, but it's really GMT that's going to open this up. And really because GMT with the right instrument can observe Roman is going to discover a huge number of high redshift quasars, but I think it's going to be fun for lots of other science too, right? Looking at stellar spectroscopy of individual things out to 250 kiloparsecs from the Milky Way, taking spectra of everything that, transient that Rubin will discover. Like, there's so many opportunities, but I think for this particular science, it's quite impactful as well. So with that, I will end. Thank you so much.
Do we have questions? Charles?
First of all, thank you, and thank you for joining GMT. So
You're welcome.
Can you hazard a guess or even a calculation of what fraction of the total heavy element abundance is already made by these redshifts?
Of the total heavy element abundance?
Today.
It's a small fraction of today's total heavy element abundance, but I don't have a number.
Will you have a number?
Yeah, I think we can do that.
I don't have to hold my breath.
I don't think that we have to have all the galaxies to calculate that number. One of my collaborators, Ron von Bordeloy, has looked at this for oxygen-1 systems and calculated that roughly half of the oxygen-1, those are actually closer to galaxies because they're much denser. Roughly half of those are around systems that we can see the galaxies, and half of them are coming from something else. But that's different from the question you're asking, which is, of all the elements that we see today, whatever it is, 2% if it's solar, but yeah, I just haven't done it.
Right.
I think we have all the information we need to calculate that.
Okay. Great, thank you.
Yeah.
Other questions? Yeah.
Yeah, thank you for the talk. I think you might have answered this sort of at the end here, but I think what you're saying is that the IGM is full of metals, like heavy metals, even when it's largely neutral and all these galaxies are quite small. So I guess my question is just how did those metals get there?
So the binding energy of all those halos is extremely small. Like, you don't have to get to a very large velocity in order to escape from those halos. And you only have to make it 10 or 15 kiloparsecs before you're in the Hubble flow, right? So it's not like the late time halos that are 100 times bigger and you've got to go 20 times farther before you're in the IGM. Like it's actually pretty easy to get there, and it doesn't take that long. And then once you're in the Hubble flow, that will just carry you. And that's pretty different. Now, to Charles's point, like that might not be a huge mass of heavy elements compared to what we see in the low redshift universe. And it's probably the case that many of those will then fall back and merge into future galaxies. And whether they actually make it all the way back into the ISM to form stars, or whether they just sit out in the halo and are cycled through some sort of precipitation and heating cycle, I couldn't tell you. But yeah, it's a good question.
Other questions?
Yeah. Just throw it up there, yes.
A really interesting talk. One, where did that velocity come from that you assume for the wind? It's the 100 and something kilometers per second.
Oh, yeah, sorry, I really elided over that. So I mentioned that program where we observed quasars, or galaxies behind the quasar to look for IGM transmission. And so for that, we had to go deep enough with NIRSpec so that we could actually detect the continuum of all those galaxies. And what that means is we could stack those spectra from a very related but slightly different program and measure the offset of interstellar absorption lines in those galaxies from the systemic redshift that's established by the oxygen-3 emission. Okay, so the carbon-2 is flowing out from those galaxies. And this is a standard thing that's been done at redshift 3 and other redshifts, where you can infer that if you see absorption that's covering the whole galaxy, what you're seeing is a wind that's being pushed out from some energy source, likely star formation, towards the Earth. Yeah, carbon-2 and silicon-4 were the strongest ones, but we've measured several different ions. Carbon-4 also, but it has emission too, so it's messy.
My point was kind of thinking, if there's a multi-phased wind, that a hotter component of the wind could be moving considerably faster than the carbon-2, for example.
Absolutely, yeah.
And
that only strengthens that argument, yeah.
could enrich further out.
Oh, I see. So if V initial was higher,
Yes.
then maybe it would go further. Yeah, that's a good point. It would have to cool along the way in order for us to see it later on. It's magnesium too. So yeah, that's a really interesting
Or
point.
cold gas gets accelerated further out where you can't detect
Yep.
it, maybe.
No, thanks for that. That's good.
Other questions?
Great talk, and since you just had dust all over the place here, Phil. On the faint companions or the dusty galaxies, isn't that a bit of a chicken and egg problem? Because the dust obviously is coming from the heavy elements. So something must have created the heavy elements to make the dust, to make the heavy elements. Any solution to this?
I don't know, you'd ask Fengwu Sun, right? So that paper, I think, was just fascinating, and I don't have an answer to that. I do know that in certain environments, like once you start making metals, the things proceed very quickly. But yeah, you don't have lots of time for AGB stars to slowly puff out dust and all those things. That's not my area of expertise. The only reason that it really emerged for me is that we found an example of one of these where there's a foreground absorption system in a lower luminosity quasar at redshift 7.25 or so, and there was no host, and then somebody found it on ALMA in dust continuum, and then went back and got a carbon-2 redshift. It is completely invisible to NIRCam. And so we know this is happening at some level. We just don't know how prevalent it is. It's it kind of surprised me, and it's surprising is always interesting.
I liked your description of LLAMAS, and I'm looking forward to using it. My students got some time in it. But I wanted to ask you, GMT, what would be your ideal instrument on the GMT to further this science? So, chemical budget of the universe. What would you need?
So I think that if you look at the GMT instrument complement, I think there's a gap that occurs sort of in this space here, right? And so I mentioned earlier that a resolution of 10 to 20,000 is interesting. We built FIRE for Magellan to have a resolution of 6,000. I think if you have more glass, you'd go to slightly higher resolution. Also, there's better infrared detectors now than there were when we built FIRE. I think you don't really want to compete with JWST out here, you're going to get creamed. But if you are around here, I think there's a lot of hay that you can make with a GMT. I think if you're going to make something that's an R of 10,000 and sort of occupies this space, you might as well go all the way down to the atmospheric cutoff, because there's other kinds of science that are very interesting to do. But I think something that, well, what's of interest to me is something that covers the infrared, goes out to the 2.5 microns, where most of the detectors end and the K-band ends, but you're kind of losing to JWST out there, but really focusing on trying to have something that either works in natural seeing so that you don't have to wait for the AO system, or that works with ground layer AO so that you just get better seeing all the time over this whole sky. And then if you can, go as far as you can to the blue, because then it becomes a very interesting instrument if you can do, you know, UZRI, GY, JHK. That's just its own kind of thing. But that's the kind of thing, you know, that's just me, right? And I think we really have to have that conversation about whether that's the right thing. That's like a reference design in my mind, but I think it would be very interesting to have that discussion and figure out what the community really wants, knowing that we both benefit from and compete with some of these things here. And I think that's a conversation GMT hasn't had in a while. So it's you know, it's timely to do that right as things are heating up.
Yeah, and I can imagine other science cases for that type of instrument as well.
Oh yeah, yeah.
Okay, maybe one more, and then we should wrap it up.
Okay, so heavy is a very imprecise description. Do you see anything as heavy as iron, for instance?
Oh yeah, yeah. I think iron is the heaviest thing we see. We see aluminum, but aluminum's lighter than iron. Mm-hmm. So nothing past the iron peak.
Okay. Thank you.
At these redshifts, it's really hard, right? It's you know, you can see them in stellar abundance patterns in the Milky Way and other places, but it is, you know, we're dealing with much lower signal to noise and much lower resolution. But iron 2 is everywhere. Yeah. Yeah, you might wonder, where did all that iron come from? I'm not going to answer that question.
Okay, we'll let you off the hook on that one. So let's thank Rob again.